Yeah, thank you for the thanks for the invitation. So today's topic is about commensurabilities of some subgroups in PU1N, and the most interesting ones are lattices. So this is a joint work with Zhiwei Zheng. He is in BIMSA right now, and he will be in Tsinghua in the fall. All right, so first, I would like to talk about some classical geometry or group theory. So there is a well-known classification of Platonic solids. So there are 5 of them: tetrahedron, cube, and the rest 3. So the classification of this Platonic solids is related to a symmetry group gamma inside O3. So when we talk about discrete subgroups in O3, or when we classify finite subgroups in O3, we will come across these geometric objects. So all the symmetry groups will be realized as either the symmetry of regular n-gon or the symmetry of those Platonic solids. So they're all included in this theory of triangle groups. So if we look at one of them, for example, let's look at the symmetry group of tetrahedron, and we look at its fundamental domain. When it acts naturally on the 2-sphere, we will find that the fundamental domain is actually a spherical triangle. So the construction is as follows. We take the vertex, one vertex of the tetrahedron A, and B is the center of a face, and C is the center of one edge. And we connect these 3 points using the big circle on the sphere. We will find a spherical triangle. And one interesting thing is that on this triangle, the angle at each vertex is pi over some integer, is in this form. So in this example, is 3 angles are pi over 3, pi over 3, and pi over 2. And from Gauss-Bonnet, we know that the sum of the angles will be greater than pi, and the deficit is exactly the is related to the curvature and area of this triangle. So it's greater than pi in this case. And for the other 4 Platonic solids, we can find a similar picture when we use vertex, the center of each face, and the center of each edge. We can form this kind of triangle. And those triangles has like 2 other cases. One is for cube, has angle pi over 4, pi over 3, and pi over 2. And the last one is the dodecahedron, is pi over 5 plus pi over 3 plus pi over 2. And for regular polygon, when we talk about the dihedral group, the symmetry group of a regular polygon, it can also be realized as subgroup of O3, and the fundamental domain is this triangle. So we just take the north pole, this is the north pole, and we take 2 points on the equator. We can form this triangle, and the angles are pi over 2, and pi over m. So the sum is also greater than pi. So put this in more uniform form, we can form any triangle on the sphere, but we require the angles are pi over some integer, some positive integer. And we know that 1 over p plus 1 over q plus 1 over r is greater than 1 from Gauss-Bonnet. And the symmetry group for these geometric objects is formed or is generated by the reflections with respect to those edges, or with respect to those big circles or geodesics on the sphere. So for example, in the first example for tetrahedron, we can use 3 generators of reflections to generate the symmetry group of tetrahedron. And the fundamental domain will be this triangle. So automatically from the classification, we know that in this case, this group is a discrete subgroup in O3. And if you take any other triangle, it doesn't satisfy this condition, like 1 over p, or these angles are pi over some integer, then it may not generate a discrete subgroup in O3. So in this case, we know that they are discrete subgroups. And if we use this triangle and use a symmetry to reflect them, then we can form a tiling of the sphere. So very natural generalization for this kind of structure is to consider the flat plane instead of the sphere. Then we can form a group, and this group will be an infinite group. So we can also take some triangle. For example, we can take the regular triangle. So each angle is just pi over 3. And in general, we can use some triangle, and the angles are just pi over p plus pi over q plus pi over r, and is equal to pi. So there are exactly 3 solutions for this equation. And the corresponding group generated by the reflection with respect to those excuse me, those straight edges will form the discrete subgroup of isometric group of the plane. And this form a special class of wallpaper groups. So it can form this kind of pattern, beautiful pattern or tiling of the plane using those triangles. And the most interesting cases come from hyperbolic geometry. So we can find infinitely many solutions for the corresponding equation or inequality. So this is one of the examples by Coxeter. So this is a tiling of the hyperbolic ball of 1 dimension, or upper half plane if you prefer. Then on this hyperbolic ball, we form all these triangles, and the edges are just geodesics on the hyperbolic ball. And from the curvature condition, we know that if each angle is just pi over p, pi over q, and pi over r, then 1 over p plus 1 over q plus 1 over r is less than 1. So the reflections generated by this edge will also form a discrete subgroup in isometric group of H2. And now in this case is a non-trivial theorem to prove that those reflections will generate a discrete subgroup. So if you change the triangle to some other triangle with some other angle, then you may not form this discrete subgroup. So this is 3 different cases of triangle group. So in the spherical case, in the flat case, and in the hyperbolic case. And we are also interested in the subgroups which preserves the orientation of the geometric objects. So this is a index 2 subgroup called von Dijk group. Is orientation preserving subgroup in this case is inside PSL2R, the conformal isometry group, or the biholomorphic automorphism of the upper half plane. So one example, classical example, is just a modular group, PSL2Z, and you can see its fundamental domain for this PSL2Z. The usual picture is formed here. And if we consider the corresponding triangle group, then the fundamental domain is just half of it, is this triangle. And you can see that it has a cusp at infinity. So the angle there is just a 0. So in hyperbolic case, we can also allow those PQR to be infinity. And the corresponding rotation map will be just translation. In this case, it's just the rotation generated by 2 reflections. It's just a translation by 1 in the x direction. And this is related to the moduli of elliptic curves. And you can see that in many examples of different geometric objects, you can see this kind of triangle group that will appear as a monodromy group of some geometric objects. And the most important, or we studied a lot about the monodromy groups of the corresponding period integral or hypergeometric functions. And then you will see this kind of groups rises in those as those monodromy groups. So when we have this kind of discrete subgroups or subgroups inside acting on some geometric objects, then we can ask the arithmeticity of those groups. For example, this group DPQR is a infinite subgroup inside PSL2R. So you can talk about whether it's an arithmetic group or not. For example, for PSL2Z, it can naturally appear in the moduli space of elliptic curves. So it has a modular meaning and is automatically an arithmetic subgroup. So the classification for triangle groups, especially for the hyperbolic triangle groups, the arithmeticity problem was solved by Takeuchi in 70s. And there are finite many. So there's a finite list of those groups. So those groups are arithmetic, and all the others are non-arithmetic groups in PSL2R. And another interesting question or important question about the classification of those groups is to classify them up to commensurability, or if you want to view it as moduli space. For example, in this case, if we consider the alpha plane quotient by this triangle triangle group, then the quotient space we can classify them, or we want to classify them up to finite cover. So the definition for commensurability for 2 subgroups inside of group G is as follows. So this is usually called the commensurability in the wider sense. So we allow conjugation. If there is an element G inside this ambient group such that the G conjugate of gamma 1 intersect with gamma 2 has finite index in gamma 2, in both gamma 1 and gamma 2. I should say in gamma 1, G gamma 1, G inverse, and gamma 2. So it has finite indices in both groups. So up to conjugacy, it means gamma 1 and gamma 2 share a common finite index subgroup. So we denote them by gamma 1 comparable with gamma 2. So this is an equivalent relation, and we want to classify those groups up to commensurability. And for hyperbolic triangles, this is basically something related to geometry, hyperbolic geometry. So for example, we can look at the modular group delta to 6 infinity. It has this fundamental domain here. And we can use one reflection to form a larger triangle. And this triangle will have infinity as one vertex, and the other 2 vertex will have angle pi over 6 and pi over 6. So this proves that the modular group contains a subgroup And these two triangle subgroups, two triangle groups will have this commensurability relation, and the index of these two groups is just 2. And we can also reflect this triangle with respect to the other edge. For example, we can reflect it according to the circle, and we form another triangle, and this triangle will have 2 cusps, and the other angle will be power 3. So it also proves that delta 3 infinity infinity will be another index 2 subgroup inside delta 2 6 infinity. We can find also some common subgroups for these two. So these two will be also commentable. So up to finite cover, we will see that they form the same group. So for arithmetic subgroups, this is also very important because, for example, when we consider Schumann variety or consider the arithmetic group, we will take all the congruent subgroups and look at the inverse system formed by those subgroups, and all those candidates will be commentable with each other. So for non-arithmetic subgroups, this is also a very important question, or a very natural question to in the classification of those groups. All right, any question for this part? So if no question, let me go to the next part of today's talk. So the first part is more or less about the geometry. Then next part, I will describe an algebraic way in which those groups appear. So the first important or classical example is just related to pure integral or hypergeometric functions. So Euler studied this kind of functions defined by this power series. It's called hypergeometric function. And this notation, an, is just a times a minus 1 up to a minus 1, n plus 1. It's like the factorial. And c is not a negative or 0 integer. So this function satisfies a second order differential equation. It's also called a hypergeometric differential equation. And since it's second order, and also it has regular singular points at 0, 1, infinity, we have two solutions for this equation. And these two solutions will be analytic will have analytic continuation on the complex plane, except 0 and 1. So it may have some singularities at 0 and 1. But if we just consider the germ of these two solutions, for example, a local expansion of the power series at some point except 0, 1, and infinity, we can talk about two solutions. And we can look at the quotients of these two solutions. So this was first studied by Schwarz. So his motivation is that these quotients, whether this quotient is a algebraic function or a rational function, or the quotient of polynomials with respect to x. So this is a multi-valued map defined on P1 minus some 3 points up to onto P1. And the monodromy of this solution of hypergeometric function will give you an representation, since the solution space has dimension 2. So the monodromy representation is just from pi 1 of 3-punctured sphere into PGL2C. So image of this monodromy representation will be denoted by gamma. So in this case, we can also see 3 different categories of or 3 different cases of monodromy representations. So the first one is gamma acting on the sphere, and it may be finite, then in this case, it's exactly the cases Schwarz wanted to study. So it's a case such that the Schwarz map is an algebraic function. And the second case is a Euclidean case. So gamma may act on the complex plane. And the last case is that gamma fix a hyperbolic ball inside P1. So the target is P1. So it fixes a hyperbolic ball inside P1. So this gamma, notice that it may not be discrete. So it's also a very interesting question to classify whether or in which cases this gamma is discrete. And when this is discrete, gamma is always committable to a triangle group. So essentially, we can reduce everything to some basic cases, and those basic cases also corresponds to the previous classification of triangle groups. So one example is also from a theory of elliptic curves. So when we look at the Legendre family of elliptic curves, then this famous hypergeometric function will appear. So it can be written as this period integral. And the monodromy group of this period integral will have log singularities, or you can see, you can call them translation monodromies at 0, 1, and infinity. So the corresponding group will be d infinity, infinity, infinity. And a natural generalization of this period integral or hypergeometric differential equation is just keep adding those variables or the singularities of these differential forms. So if we consider a differential form in the following form is dz over some expression like d minus dj up to mu j's power, and in order to integrate this this differential form from zi to zj, then we require those Paul order mu I to be less than 1 and greater than 0. So when it's greater than 1, then the Paul order is too large. We cannot do this kind of we cannot have a well-defined integration from zi to zj. And when this mu j is less than 0, then we can view it as some regular points. So we put this natural requirement for those denominators. So mu j is from 0 to 1. And we can also consider mu j to be irrational numbers. But for now, let's just consider those as rational numbers. So we can integrate this differential form on the complex plane from zi to zi plus 1, and it will form a multi-valued function with respect to the parameter z1, z2, and up to zn plus 3. So this is a multi-valued function. Of the poles z1 up to zn plus 3. And the previous case corresponds to actually corresponds to n equals 1 because up to after a change of coordinates, you can see that the pole order of this differential form, the poles of this differential form are actually 0, 1, x, and infinity. So it also has a pole at infinity with order 1/2. So we study this kind of functions, and if we connect all the poles, then essentially we just need n plus 1 of those arcs to express all the other integrations. So if you have another path, you can express it as linear combinations of these functions, and they are classically called Lauricella functions. And now what we want to study is the symmetry group arising from these multi-valued functions. So this will be a system of functions, and the monodromy group will be some subgroup inside PGL n plus 1. So first, let's describe the modular space in which on which these functions define. So we can always use PSL2C to move D1, D2, D3 to 0, 1, infinity. So we can assume those points are distinct, and the first three are 0, 1, infinity. So we have n free variables, and this Q will be the modular space or the parameter space for those functions. And the monodromy of those meromorphic functions will give us a monodromy representation into PGL n plus 1C. And one important generalization of the classical theory for 4 variables, or from Schwarz theory, was studied by many mathematicians, and in the 80s, Deligne-Mostow and also Thurston has a uniform treatment of this theory. So I will only describe the part about hyperbolic case. So they also have the spherical case or the flat case, but the most examples appear in the hyperbolic case. So the hyperbolic case corresponds to the sum of those mu I equals 2. So if the sum of these rational numbers is equal to integer 2, then the image of this monodromy representation will be a subgroup inside PU1N. So what is PU1N? PU1N is a subgroup of PGL n plus 1C, which preserves a form, a Hermitian form of signature 1n. So when n is equal to 1, the PU11 is just a group PSL2R or PSO21. They are all isomorphic. You can view upper plane as a complex hyperbolic space of dimension 1 or a real hyperbolic space of dimension 2. So there are different points of view to see upper plane. But for n greater or equal than 2, then these these groups are different. So for n equals 1, this map or this monodromy representation corresponds to Schwarz theory. And for n equals 2, Picard studied this kind of group, and the quotient of complex hyperbolic ball by this monodromy group is called Picard modular surfaces. So next, let me explain a little bit why this kind of monodromy representation will preserve a Hermitian form. What's the natural structure coming from this Hermitian form? So I will take Thurston's approach. So Thurston's interpretation of this Hermitian form is as follows. So remember that we have this differential form with some poor order. Let's say at Ci has this rational poor order mu I. And if we take its bar, dz bar, then it will form a flat metric on P1 with some singularities at those points Z1 up to Zn plus 3. And a local study of this kind of metric local model like this will tell us that the angle for those singular points is less than 2 pi, and the deficit of this angle is equal to 2 mu I times pi. You can also view this as a curvature of this singular metric, and this curvature is positive, since sphere has a positive order characteristic. And then Gauss-Bonnet tells us that the condition about mu I is just a Gauss-Bonnet theorem, which means that the sum of those contribution of curvatures at each singular point will give us 4 pi. And in this case, it's just a sum of mu I is equal to 2. And this is why we have this condition, sum of mu I equals 2. And we also call this convex case because the angle there is, the cone angle there is less than 2 pi. So if you just form a model of this kind of conic metric, it will be some convex polytope. Looks like some convex polytope. So why we have a Hermitian form? So the Hermitian form naturally comes from the area of this metric. So this Hermitian form comes from the area of the metric. So let me explain why is that. So if we have a flat metric on the sphere, then we can cut this sphere using some straight edge. For example, if we connect all these edges from Z1, D2 to Z2, D2 to Z3, and up to Zn plus 1, we have n plus 2 edges or n plus 2 arcs. And if we use scissors to cut this sphere using these arcs, and we cut along the geodesics or the straight lines, and then we can flatten this or put this sphere locally on the flat plane. So this just formed by this developing map. So more explicitly, it's just an integration of this differential form from some vertex point or from some fixed point to the point Z on the sphere. And this developing map, the image, you can imagine that it may have some overlap, but let's consider the most simple case. It doesn't have some overlap. Then we flatten this surface, we cut this surface and put it on the plane. Then it will form a polygon on the plane. And from the convex condition, it will be a convex polygon. So the angles are related to the mu I we're choosing. So it has 2 times n plus 2 edges, and those edges will be some complex numbers. For example, the first edge is just integration from Z1 to Z2 of this omega. And the second edge, you need to rotate the corresponding angle and then do the integration. So that's a complex coordinate for the second edge. And you can accumulate those angles and then form all these edges and comes back. So it has n plus 2 pairs of those edges. So it can form this edge and it can come back to the original point. So the sum of these complex numbers will be 0. So it will satisfy one linear relation. So it will come back, sum of those will be 0 since it will form a closed loop. So this is why all these integrations actually has n plus 1 free variables instead of n plus 2. So it can form a n plus 1 complex linear subspace. And the Hermitian form defined in this case is just an area of this polygon. So this convex polygon will have parameters like this edge, and the area will be function of the edge. And why this has signature 1n, we can complete this complex polygon. For example, for this let's see, 1, 2, 3, 4, this 8-gon, we can always complete to a 4-gon. And when we complete the polygon, we can use the total area to minus those triangles. So when we complete it, we can form those triangles. And each time when we minus those triangles, it will add some signature to the negative part, because area is always positive. So when we minus them, we will have some negative part. And finally, it can reduce everything to just one polygon with just 4 edges or 3 edges. And this can prove our theorem by induction. All right, so this explains that the monodromy of those generalized hypergeometric function will have monodromy inside PU1n. So the next natural question from Schwarz theory is that when those groups are discrete, and when those groups are arithmetic, and when those groups are comparable to each other. So there are 3 natural questions related to these functions or this monodromy group. So the first criterion for discreteness or complete list for discreteness was obtained by Deligne-Mostow, the paper, and also later Mostow's paper. And Thurston also gave another interpretation. But Thurston, the paper published in the 90s, I think, yeah. So there are different approaches. Thurston's approach is more geometric. So the complete class list of those discrete subgroups was obtained in Mostow's paper. So 94 of them satisfy some condition they called half integer condition, and there are 10 exceptions. And for n equals 1, there are infinite many of those groups, and basically they are all related to triangle groups. And for arithmeticity, for n equals 1 is already done by Takeuchi. And for n equals 3, there is one non-arithmetic subgroup inside PU 1, 3. And for n equals 2, there are 18 examples for those parameters. So since n equals 2, this PU1, this is PU1n 1, 3, and for the others are PU 1, 2. There are 9 commensurability classes of non-arithmetic. So this is non-arithmetic. Those non-arithmetic groups inside PU1, 2. So for n equals 1 and n greater or equal than 2, the behavior is quite different. For n equals 1, there are infinite many non-arithmetic groups, and for n equals n greater or equal than 2, there are only finitely many of them. And another interesting example was obtained by Dirac, Parker, and Poppert. They find 12 new commensurability classes of those groups inside PU1, 2. So it's not given by this Deligne-Mostow theory or this parameter mu. It's given in some from other given in some other forms. One remark why we care about this. This is also one of the most important motivation from Deligne-Mostow theory. So SU1n or PU1n is the only simple Lie group such that we don't know how many non-arithmetic lattices in there. So for the case of n greater or equal than 2, equal than 4, we have no example of non-arithmetic lattice. We don't know whether it exists or not. And for n equals 2, there are only finite examples I mentioned above. And for all the other simple groups, for rank greater or equal than 2, Margulis super rigidity theorem tells us there are no non-arithmetic lattices. So all the lattices are automatically arithmetic. This is a very deep result obtained from ergodic theory. And for rank equals 1, for O1n, we know infinitely many of them from construction by Gromov and sorry, I forgot the name. Gromov and another collaborator. And for SU1n, we know some finite examples, but we don't know whether there are infinitely many. And for others, there are results similar to superrigidity, saying that there are no non-arithmetic lattices. So in some sense, SU1n is the only case we don't know whether we can construct infinitely many non-arithmetic lattices or not. So this is so their motivation is to construct those non-arithmetic lattices. And actually, Deligne-Mostow's paper is the first example constructing those non-arithmetic lattices in PU12. So the last question, and also related to the results I want to report today, is about the commensurability classification of those groups. So for n equals 1, again, it was done by Takeuchi for triangle groups. And for n equals 2, there are some results by Sauter, Deligne and Mostow. So it's Sauter's thesis when he obtained his PhD with Mostow under the supervision of Mostow. And they provide some examples of commensurability relations to for those groups, gamma mu and gamma mu prime. So if we choose some parameter, so these are subgroups inside PU12. So they may not be discrete. So not necessarily discrete. So their result also applies to non-discrete examples. So the first example, or their theory or their results are classified in two categories. One is has two parameters, A and B. So mu is equal to AABB and 2 minus 2A minus 2B. And the other one is in this very weird form. And the other example involves just one parameter. And the formula is as follows. So they prove that these two groups are compatible to each other in PU12. So this result is used in their classification for discrete subgroups in PU12, because for those 10 exceptions, in order to prove it's also discrete, they cannot apply this half integer condition. It doesn't have a uniform proof, but from their commensurability results, they can prove those are commensurable to some of the known non-arithmetic groups, or their arithmetic groups, and then they are automatically discrete. So these two categories or these two results are important in the classification result. And let me use the rest of the time to report our main results in this direction. So this is a collaboration with Zhiwei Zheng. We have a list of commensurability for those groups in the Mostow theory. So for n equals 3, we have two infinite lists of examples. So we have n equals 3. So we have 6 tuple, and mu and mu prime are related in this form. And for n equals 2, we also recover or reprove Sauter and Deligne-Mostow's results by a different method. And for n greater or equal than 4, we have 6 pairs of those groups, those commensurability results. So let me explain how we obtain these results. So these numbers may seem very weird. So it does seem weird to me when I first came across this kind of result. And when I read Sauter's thesis, it told us how they obtain those numbers. So first, Mostow has a theory about complex reflection groups. So it's mainly inside PU12. So he studied the subgroups generated by complex reflections, especially generated by 3 complex reflections. And he could find some description of the fundamental domain and use computer. He found some interesting behavior of those fundamental domains, especially the boundary of those fundamental domains. And those similarities inside those fundamental domains helped him to find or conjecture some pairs of those mu will have commensurability relations. And then in Sauter's thesis and later in Deligne-Mostow's book, they wrote down the rigorous proof based on comparing those 2 modular spaces quotient by some permutation subgroups, and then compare those surfaces with divisors and also some other monodromy data associated with those divisors, and they prove that those groups are isomorphic. So their results is from the study of those surfaces, and I think it may be hard to prove those results in higher dimensions because geometry will be much more complicated for threefolds and high dimension modular spaces. And our approach is different, and our approach is to relate this period integral, those period integral on P1, cycles on P1 of this singular form, to a period integral in dimension 2. So it will be a 2 form, and cycles will be cycles inside P1 cross P1. So let me explain how these 2 integrations are related. So the background are some algebraic geometric constructions. So in the Mostow theory, they already know how to realize this, or classically, people already know how to realize those period integral on P1 to homogeneous curves. So this also appears in the introduction of Riemann surfaces, or the original motivation for Riemann to study those functions or construction of Riemann surfaces. So for each mu, we can consider this kind of curve is a cyclic cover of P1 with ramification locus Z1 up to Zn plus 3. And the ramification data are given by this mu I. That's why in this case, we require those mu I rational numbers. Oh, sorry, this is 1 minus mu I times D. We use a common denominator of those mu I's. And then this group action will decompose the cohomology of the curve into character spaces. And the tautological character space, so chi is tautological character. And the tautological character space will have a Hermitian form of signature 1n, and its restriction to H10 part is always positive. So this relates to the original construction. We're saying that the area is always positive. So that's why it has signature 1n. And this monodromy representation of corresponds to the Hodge structure so this forms a C Hodge structure on the character space. And this monodromy representation will be into PU1M. And this corresponds to the monodromy representation of those Lauricella functions, or the period integrals. And we consider some surfaces related to the Mostow theory. So our construction is to consider this surface instead of curves. They are cyclic covers of P1 cross P1, and their ramified locus are curves instead of points. So we have a J action on S, and we look at the second cohomology of S. And this S will have two different fibrations, potentially different fibrations onto P1 and by the projection to P1. And we can relate this cohomology of S to the curve. So we have some curve C mu1 and C mu2 to P1, and we can relate this cohomology of surface to the cohomology of these curves by the projection. And there are some conditions, of course, there are some conditions such that we can relate this. And if this kind of condition, numerical condition, are satisfied, then the monodromy representation of mu1 and mu2 will have a subgroup, finite index subgroup coming from the monodromy representation from the moduli of S. So we find some common finite index subgroups inside these monodromy representations. So that's why we can relate these two. So these image are comparable. And the numerical condition is not very hard. It's just a summation of the degrees is equal to 3, and the weighted degree or the mu I times the degree of Fi is equal to 2. So it's a generalization of the original Deligne-Mostow system condition. And we can also consider some subcases such that this curves, the branching curves, has some singularities or some special positions. And using this numerical condition, we can give a complete classification of those examples. And then those examples will give us pairs of mu1 and mu2. So let me give you some examples. The most simple example is just 1f. So degree of f is equal to 3. So it will be a degree 3 curve inside P1 cross P1. And then this is a classical theory. If we take P1 cross P1 into by the Plucker embedding into P3, then it's a quadric inside P3. And we know that for a smooth generous 4 curve, non-hyperelliptic, this curve is always a complete intersection of a quadric with a cubic inside P3. So in other words, it's a degree 3 curve inside P1 cross P1. And in this case, the two parameters are actually symmetric. So we obtain two identical Deligne-Mostow data mu. So they all correspond to 12, 1/6. So there are 12 of them. And we can consider some degeneration of this example. For example, if we consider F1 is a degree 3-2 curve, and F2 is a 0-1 curve. Oh, I forgot to mention here, D is equal to 1, A1 is equal to, D is equal to 3, A1 is equal to 1. So it's equal to Y cubed F1 times F2. So this is a degeneration of the first example. And for this, we know that this is not symmetric anymore. So the illustration of this configuration is as follows. So F1 equals to 0 will give us a 3-2 curve, and F2 equals to 0 will give us one line, horizontal P1. And then the singularities for the fibration of S1 maps to S2 maps to P1 and two projections will be different. So if we project down to the X variable, then we need to consider the branching point of F1 equal to 0. So there are 6 of them. So 6 of them of this kind of branching points. And there are 3 intersection points of f1 equal to 0 and f2 equal to 0. So the monodromy data or the Deligne-Mostow data we obtain is just 1/6 and 1/3. And for the other projection direction, for the branching point, ramification points, we also have 1/6. And for this vertical line, horizontal line, we will have 2/3. And this example is also very interesting because it's a case-free surface, and it's a but it has a bi-elliptic fibrations. And this first example was first studied by Kondo. And the next example is the example we recover Sauter Deligne-Mostow's result. So in this example, we have 4 curves with a corresponding degree 2, 1, 1, 0 and 0, 1, 0, 1. And the equation or the numerical condition we're given just equivalent to this one. So by solving this equation, we have 4 parameters and 2 equations. So we have 2 free variables, and those 2 free variables will give us the 2 parameters in this mu1 and mu2. So from this point of view, we can see why we form or why we have this combination of the 5 tuples in Sauter and Deligne-Mostow's result. So the corresponding picture of the intersection of those curves and the singular points is in this picture. So for the last 4 minutes, we mentioned the other classification, commensurability classification. So the classification of the discrete cases is almost done. So for the non-arithmetic cases, Sauter and Deligne-Mostow's result relates some of them, but people didn't know whether those are the all commensurability results. So we need to find some commensurability invariance to distinguish those examples. And it was a result of Capes-Muller, and also later Macmillan has a simpler formula. So the original motivation was to study Lyapunov exponents for flat surfaces, and Macmillan's motivation is more about the volume or the Gauss-Bonnet theorem for modular spaces. So anyway, their invariants are just some Chen numbers by Galois conjugation. So the ratio of, I should say, ratio of Chen numbers by Galois conjugation. These are commensurability invariants, and they distinguish those non-arithmetic cases. And from joint work with Zhiwei Zheng, we also has a classification for arithmetic cases. So it's I should say it's known to experts, and the invariance should be the Hermitian form corresponding to those arithmetic lattices. And our approach for the commensurability relations, instead of just consider the arithmetic groups or the Hermitian forms, is that our commensurability results also obtain some commensurability index or the bounds for commensurability index for those groups. Right, that's all I want to report today. Any questions?
Yeah, thanks for the talk. So any question for the speaker? Yeah, if you have any question, you can unmute by yourself or type it in the chatting. Okay. Yeah, probably let me ask a question. So it seems that you are trying to relate the something like the Hermitian form also to the representation of the fundamental group. Am I understanding correct?
Yeah.
I think probably, yeah. I think when you state the mean result, you are writing down it seems that the fundamental group of Q mu mapping to the PU1n, it seems to be related to the Hermitian metric, right? Or Hermitian forms.
Yeah, so those Hermitian forms, those two representations also preserve the Hermitian form. So that's why the monodromy representation is into PU1n. So a priori is just in the PGL n+1c.
Okay, so is it something like a version of narrow simultaneous correspondence?
But
actually, for narrow simultaneous correspondence, they consider the holomorphic bundle and the relation with the representation of the fundamental group. I'm not sure, because here it seems that you are considering something like a real Lie group. Actually, I'm not very familiar with PU1n, but it seems to be something like a projective group with the real form U1n, something like that. But I'm not sure whether it can be understood in this way.
So I think so for the Deligne-Mostow series, there also some like stability condition involved, some like moduli space from GIT, and the other side is moduli space corresponding to symmetric spaces. So I think let me see. So when you construct or compare the two moduli spaces, one side is moduli space of points on P1. Then the natural compactification involves GIT stability condition. And the other side is just a complex hyperbolic ball. So I didn't mention the period map. So it's a Hermitian symmetric space.
Yeah.
And it's a non-algebraic. So there's no algebraic structure on it. But when you quotient by those monodromy groups, then it has a natural algebraic structure, and also has a natural compactification, Bailey-Borel compactification or toroidal compactification.
Okay.
Yeah, and from the Mostow theory, more or less you have this kind of correspondence from stability condition to this natural compactifications, and the corresponding data or the moduli meaning is also explicit in their theory. So if you want to view this kind of thing, like some similar thing in Narasima Sassedri, it's just when you consider the solutions to differential equation or flat connections, then you have some degeneration, and you want to add those degenerate objects in order to have a nice compactification. And if it's already compact, then the stability condition just corresponds to the solution of those equations, and you don't have any degeneration. And for the Mostow theory, there are some cases with no degeneration, and also most cases has some degeneration.
Okay. Thanks. Okay, so any other question? Yeah, if there is no question, yeah, let's thank the speakers again. Okay, so